in something that, it turns out, literally cannot exist. A 3x3 grid where every single cell is a distinct perfect square and every row, column, and diagonal adds up to the same number. People have searched for it, computed for it, and dreamed about it. And a new proof by mathematician Shaimar Saeed Sultan has finally closed the case, not by finding it, but by proving, algebraically, that it is impossible. Today, we're breaking down that proof, what a magic square of squares actually is, why the algebra creates an inescapable in its 425 squared example, the closest any progressive any perfect bottom really is telling us about the limits of mathematical possibility. Thus, the Navy's drivodla in squack shapu as experiment, by Shannon as ratios, but allowed it to be truth, and the index.
So a regular magic square is a grid of numbers where every row, every column, and both diagonals all add up to the same total, the magic sum. A magic square of squares takes that and cranks up the difficulty. Now every entry in the grid has to be a perfect square. So not just any number, it has to be something like 25, or 169, or 425 squared. And the question that has haunted number theorists is, can you fill a 3x3 grid with 9 distinct perfect squares and still have that magic property?
And the answer, according to this proof, is no.
Definitively no. But what makes this proof so interesting is not just the answer, it's the method. The proof by Shaimar Saeed Sultan doesn't rely on a computer search or brute force. It's a structural argument. It shows that the very algebra of magic squares creates a contradiction the moment you demand all 9 entries be perfect squares.
Okay, walk me through the setup. How does the proof even begin?
So the proof starts by labeling the 9 cells of the 3x3 grid. You have a squared, b squared, c squared across the top row, d squared, e squared, f squared in the middle row, and then in the bottom row, there's a cell called x in the bottom left, h squared, and I squared. The center cell is e squared. And the key insight is that once you fix 3 parameters, a squared, e squared, and x, the magic square structure completely determines all the other 6 cells.
Wait, so 3 numbers lock in the whole grid?
Exactly. The magic square conditions, all those row, column, and diagonal sums being equal, are so rigid that they leave almost no freedom. Once you pick a squared, e squared, and x, you can write down explicit formulas for every other cell. For example, I squared equals 2 e squared minus a squared, c squared equals 2 e squared minus x, b squared equals e squared minus a squared plus x, and so on for d and f and h.
So the grid is basically a machine. You put in 3 numbers and it spits out the other 6.
That's a really good way to put it. And one of the first things the proof establishes is this beautiful property called the opposite pair identity. In any 3x3 magic square, every pair of cells that are directly opposite each other through the center must sum to exactly 2e squared. So a squared plus I squared equals 2e squared. B squared plus h squared equals 2e squared. C squared plus x equals 2e squared. D squared plus f squared equals 2e squared.
And that's not a coincidence. That falls out of the algebra automatically?
Completely automatic. You can verify each one just by substituting the formulas. Like d squared plus f squared, you substitute in 3e squared minus a squared minus x plus a squared plus x minus e squared, and everything cancels perfectly to give you 2e squared. The structure enforces it.
And why does that matter for the magic sum?
Because every row, column, and diagonal passes through the center e squared and contains exactly one opposite pair. So the line sum is always e squared plus 2e squared, which is 3e squared. That's the magic sum. It's completely determined by the center value.
So the center is kind of the anchor of the whole thing.
The center is everything. It's the average of every opposite pair, and it sets the magic sum for the entire grid. Change the center, and the whole square rescales around it.
Okay, so we have this elegant universal structure. Now, here's where I want to push. What happens when you say, all right, I want all 9 of these entries to actually be perfect squares? That's where the trap springs, right?
That's exactly where it gets lethal. So you have the formula, b squared equals e squared minus a squared plus x. That's just what the magic square structure gives you. Now, the magic square also requires that a squared and b squared are an opposite pair. Wait, actually, let me be precise. The condition that closes the square is that a squared plus b squared must equal 2e squared.
Okay, so you have 2 equations involving b squared.
Right. You have b squared equals e squared minus a squared plus x from the structural formula, and you have a squared plus b squared equals 2e squared from the magic square condition. So you substitute the first into the second. A squared plus, in parentheses, e squared minus a squared plus x equals 2e squared. The a squareds cancel. You're left with e squared plus x equals 2e squared, which means x equals e squared.
X equals e squared. The bottom left cell equals the center.
Exactly. And that's the contradiction. If x equals e squared, then you have the same value appearing twice in the grid, once in the center and once in the bottom left corner. So you cannot have 9 distinct perfect squares. The algebra won't allow it.
That's almost cruel. The structure of the magic square itself is what kills the possibility.
It's a self-defeating constraint. The more you try to force the grid to be perfect, the more the algebra pushes back and says, no, you have to repeat a value. You can't escape it.
So this isn't like we just haven't found the right numbers yet. It's not a search problem.
Not at all. This is a proof. It applies to every possible 3x3 magic square, regardless of what numbers you choose. There is no combination of a squared, e squared, and x that gets you 9 distinct perfect squares. The theorem is universal.
Okay, so if 9 is impossible, what's the best anyone has actually achieved? Because I know there's a famous example here.
Yeah, and this is where the story gets really satisfying. The best known example is the 425 squared magic square discovered by Bremner and Sallows. It has 7 perfect squares and 2 non-square entries. The grid looks like this. Top row is 205 squared, then 360721, then 373 squared. Middle row is 527 squared, 425 squared, 289 squared. Bottom row is 222121, then 23 squared, then 565 squared.
So 360721 and 222121 are the 2 entries that aren't perfect squares.
Correct. And what the proof shows is that those 2 non-square entries appear in exactly the positions the theory predicts they must. In the universal labeling, 360721 is in the b squared position, and 222121 is in the x position. Those are precisely the 2 cells that the structural equations link together, b squared equals e squared minus a squared plus x.
So the theory doesn't just explain why 9 is impossible, it also explains why this particular example has non-squares in those specific spots.
Precisely. And you can verify that the 425 squared example satisfies all 4 opposite pair identities. 205 squared plus 565 squared equals 2 times 425 squared. 360721 plus 23 squared equals 2 times 425 squared. 373 squared plus 222121 equals 2 times 425 squared. 527 squared plus 289 squared equals 2 times 425 squared. Every single one checks out.
That's remarkable. It fits the universal structure perfectly. It deliberately avoids the trap by leaving those 2 cells non-square.
And that's the key insight from the proof. The 425 squared example isn't just a lucky find. According to the paper, it is the canonical representative of all possible 7-square magic squares. Every 7-square magic square has to look like this, 7 squares, with the non-square entries in the b and x positions.
Wait, so it's not just one example among many, it's the archetype.
That's what the proof establishes. The universal equations developed in the paper show that the layout of the 425 squared square matches the algebraic framework exactly. It's not an isolated curiosity, it's the template.
I want to go back to something you said earlier because I think there's a subtlety here that's easy to miss. You said x can be a perfect square without forcing b to be a perfect square. But b cannot be a perfect square without forcing x to equal e squared. That asymmetry feels important.
It's the heart of the whole thing. So the proof actually analyzes 2 cases. Case 1, x is a perfect square, but b is not. The structural formula b squared equals e squared minus a squared plus x gives you a value for b squared, but there's no requirement that value itself be a perfect square. The magic square conditions are all satisfied, no contradiction arises. So this configuration is structurally possible. It would correspond to a magic square with 8 perfect squares and only be non-square.
8 squares, so that's actually theoretically allowed.
The universal equations don't forbid it. The structure allows it. Whether you can actually find specific numbers that achieve it is a separate question, but the algebra doesn't rule it out the way it rules out 9.
And case 2?
Case 2 is where the impossibility lives. If you require b squared to be a perfect square, then the universal identity a squared plus b squared equals 2e squared kicks in. You substitute b squared equals e squared minus a squared plus x, and you get x equals e squared. So b, being a perfect square, forces x to equal the center. No way around it.
So the asymmetry is x squared doesn't force b square, but b square forces x to equal e squared.
Exactly. And that asymmetry is why 7-square magic squares exist, like the 425 squared example, while 9-square magic squares cannot. In the 425 squared case, x is 222121, which is not a perfect square, and b squared is 360721, which is also not a perfect square. By leaving both non-square, the example sidesteps the forced repetition entirely.
It's like the square found the one loophole in the algebra.
And the proof shows it's the only loophole. You can't do better than 7 distinct perfect squares in a 3x3 magic square. That's the corollary stated explicitly in the paper. 7 is the maximum.
You know, I keep thinking about the history of this problem. Magic squares go back thousands of years. They show up in ancient Chinese mathematics, in Renaissance art. Dürer put one in his engraving Melancholia in 1514. And here we are, still finding new structural truths about them.
That's what makes this kind of result so satisfying. The question of whether a 3x3 magic square of squares exists has been open for a very long time. And the answer isn't just no, it's no, and here's exactly why, and here's exactly what the best possible thing looks like. That's a complete picture.
And the Bremner and Solo's discovery, that was a combination of deep number theory and computational search, right? It sits at this intersection of human mathematical intuition and machine power.
Right, and what this proof does is take that computational discovery and give it a theoretical home. It says, here is the algebraic framework that explains why that square exists, why it has 7 squares and not 9, and why the non-square entries are where they are. The computation found the example, the proof explains it.
That's a really nice division of labor between computation and theory.
It's how a lot of modern mathematics works. You find something surprising computationally, and then you build the theory that makes it inevitable in retrospect.
Let me ask you something that might sound naive. Why does it matter? Like, who cares if you can or can't fill a 3x3 grid with 9 perfect squares?
That's actually a great question, and I think the honest answer is, it matters because impossibility proofs are some of the most powerful things in mathematics. When you prove something cannot exist, you're not just closing one door, you're revealing the deep structure of the mathematical universe. The proof here isn't really about magic squares, it's about the constraints that algebraic identities impose on number-theoretic objects. That kind of structural insight has ripple effects.
So the magic square is almost like a test case for a deeper set of ideas.
Exactly. The techniques used here, parameterizing a family of objects, deriving universal equations, finding the constraints that force contradictions, those are tools that show up across number theory, algebraic geometry, and beyond. The magic square of squares is a beautiful, concrete problem that makes those tools visible.
And there's something almost poetic about the fact that the proof is so clean. It's not a massive case analysis or a computer-assisted proof with thousands of subcases. It's a few lines of algebra.
That's what makes it elegant. The whole argument fits in a handful of equations. You set up the universal parameterization, you derive the opposite pair identities, you apply the squareness condition, and the contradiction falls out immediately. It's the kind of proof where once you see it, you can't unsee it.
Okay, I want to make sure I have the full picture before we wrap up. So the theorem, as stated in the paper, is any 3x3 magic square whose entries are perfect squares and whose center is e squared must satisfy x equals e squared if all 9 entries are required to be perfect squares. And that forces a repeated value. So 9 distinct perfect squares, impossible.
That's the theorem, exactly. And the corollary is that 7 is the maximum number of distinct perfect squares that can appear in a 3x3 magic square, as demonstrated by the 425 squared example.
7 squares. That's the ceiling. And we know it's the ceiling because we have both a proof that 9 is impossible and an example that achieves 7.
Right. The example shows 7 is achievable. The proof shows 9 is not. Together, they pin down the answer completely. The only open question is whether 8 is achievable, and the proof shows the algebra doesn't forbid it, but no one has found an example yet.
Oh, so 8 is still an open question?
According to the structural analysis in the paper, yes. The case where x is a perfect square and b is not is structurally possible. The equations don't produce a contradiction. But whether you can actually find numbers that realize that case is a separate and apparently still open problem.
So the proof closes the door on 9 but leaves a crack open for 8.
A structural crack, yes. Whether anyone can squeeze through it is another matter.
All right, so when you step back from all of this, the universal parameterization, the opposite pair identities, the algebraic trap, the 425 squared example, what's the real takeaway here?
I think the takeaway is that mathematical structure is both more rigid and more revealing than it looks. The magic square of squares seems like a puzzle. Can you find the right numbers? But the proof shows it's not really about finding numbers at all. It's about understanding what the structure of a magic square forces to be true. And once you understand that, the impossibility of 9 distinct perfect squares isn't surprising, it's inevitable.
And the 425 squared example becomes not a near miss, but a complete answer.
Exactly. It's the canonical example. It's not the best anyone could do before finding the real answer, it is the real answer. 7 squares, 2 non-squares in the b and x positions, all opposite pair identities satisfied. That's what the theory predicts, and that's what the example delivers.
Here's what I find genuinely striking about this. We started with a question that sounds almost recreational. Can you fill a 3x3 grid with 9 distinct perfect squares? And the answer turns out to require a complete structural theory of what magic squares of squares can and cannot look like. The question was simple, the answer is deep.
That's the best kind of mathematics. The questions that look simple on the surface but pull you into something much richer when you start pulling on the thread. And the proof by Shaima Saeed Sultan does exactly that. It takes a centuries-old puzzle and gives it a complete, elegant, algebraic resolution.
And it does it in a way that's actually followable. You don't need a PhD to trace the logic. You need to be willing to sit with a few equations and let them do their work.
Which is, honestly, what good mathematical exposition should do. Make the ideas accessible without dumbing them down. The proof is elementary in the technical sense. It uses basic algebra, but the insight it delivers is profound.
So here's what this really comes down to. We now know 3 things with certainty. 1, every 3 by 3 magic square of squares is completely determined by just 3 parameters, a squared, e squared, and x, and the center e squared anchors everything. 2, demanding all 9 entries be perfect squares creates an algebraic chain reaction that forces the bottom left cell to equal the center, making 9 distinct perfect squares impossible. And 3, the 425 squared magic square discovered by Bremner and Solos isn't a curiosity or a near miss. It's the canonical representative of the best that's mathematically achievable. 7 distinct perfect squares, with the 2 non-square entries appearing exactly where the theory says they must.
And that third point is maybe the most underappreciated one. Before this kind of structural analysis, the 425 squared example could look like a lucky accident. Someone found a grid that almost works. After the proof, it looks like the inevitable outcome of a deep algebraic truth. The example and the theory illuminate each other.
Which is a reminder that in mathematics, understanding why something is true is often more valuable than just knowing that it's true.
Always. The why is where the real knowledge lives. And in this case, the why is a handful of equations that anyone can check with a calculator.
We started this episode with a centuries-old chase. Mathematicians hunting for a 3 by 3 grid of 9 distinct perfect squares that adds up perfectly in every direction. And it turns out the hunt was always going to end empty-handed, not because no one was clever enough, but because the algebra itself makes it impossible. The grid fights back, the structure wins, and the 425 squared magic square, 7 perfect squares, 2 deliberate gaps, isn't a consolation prize. It's the proof's own Exhibit A, the canonical shape of what mathematical possibility actually looks like when it hits its limit. That's Copilot Podcasts. If this made you want to stare at a grid of numbers for the next hour, we've done our job.